We looked at the small bodies that orbit around planets. Now we need to turn to the small bodies that orbit the Sun instead. The first of these are the asteroids. Asteroids are made of a combination of rock and metal, carbon-rich organic material, and in some cases, water ice. Over 100,000 asteroids are known, and several have been visited by spacecraft, as shown here. While most asteroids are tiny, only a few kilometers across, the largest ones can be several hundred kilometers across, like 4 Vesta. The vast majority of asteroids are located in a band between the orbits of Mars and Jupiter. This is one of the few places where a small body has a chance to stay in orbit around the Sun without being perturbed by the larger planets over the 4 billion-year history of the solar system. However, some asteroids do get scattered out of the main asteroid belt, and these can be found throughout the inner solar system. These inner solar system asteroids are in temporary orbits. Over hundreds of millions of years, they will either hit a planet or the Sun or be thrown out to the outer solar system to encounter Jupiter. This means that the population of inner solar system asteroids has to be constantly replenished with new additions from the main asteroid belt. The other major group of small bodies orbiting the Sun are the trans-Neptunian objects, or TNOs. TNOs are divided into 2 major groups. The first of these form what we call the Kuiper belt, which extends from Neptune's orbit, 30 AU from the Sun, out to about 50 AU. Actually, this is a simplification. Folks who study this region divide it up into several groups of bodies like the Plutonos and the scattered disk, but we're going to lump them all together into the Kuiper belt. Like the asteroids, objects in the Kuiper belt are made of a combination of ice, rock, and carbon-rich materials, though the balance seems to be weighted much more towards the ices. The largest bodies in the Kuiper belt are much larger than the largest asteroids. In fact, Pluto is a member of the Kuiper belt. So is Eris, a slightly more massive body beyond the orbit of Pluto. Since the Kuiper belt is so much farther away than the asteroid belt, we can't see anything very small there. So all the green dots you see in this map of the outer solar system appear to be hundreds of kilometers across or larger. If they were in the asteroid belt, they'd be among the largest asteroids known. The other big group of trans-Neptunian objects form what we call the Oort cloud. Several decades ago, Jan Oort proposed that there was an Oort cloud out there because of the orbits of comets. He found that many comets seemed to be coming from a spherical region extending as far as 50,000 AU away from the Sun. There may be trillions of small, icy bodies in this cloud, but they're very difficult to observe. However, we have seen a few bodies that go far beyond the Kuiper belt. The largest of these is Sedna. Sedna is in a very elongated orbit. When it's farthest from the Sun, it gets to 1,000 AU away, putting it at the inner edge of the Oort cloud. When a trans-Neptunian object is scattered into the inner solar system, something interesting happens to it. As it gets closer to the Sun, it warms up, and the ices it's made of start to vaporize. If the object were big enough, this would simply give it an atmosphere. But most of the TNOs that come into the inner solar system are small, so instead the gas they emit simply blows off into space. This cloud of gas and dust turns the TNO into a comet. The background picture here shows Comet Hartley 2. You can see where the sunlit side of the comet is spewing out gas at high speed. This will form the cloud, or coma, that we see from Earth. The solid body is called the comet's nucleus. As it gets still closer to the Sun, the effects of sunlight and the solar wind push some of this gas and dust out away from the Sun, giving the comet a long tail. So when we see a comet in the sky, this is what it looks like. A fuzzy, glowing blob, often with a tail. The coma can be up to 100,000 times as big as the solid nucleus, but it's made of very tenuous gases, mostly thinner than laboratory vacuums here on Earth. As we described earlier, being large enough to have a spherical shape makes an important dividing line in studying small bodies in the solar system, Objects orbiting the Sun that are larger than this, but too small to be planets, are called dwarf planets. These are considered too small for planets because their gravity is not strong enough to clear out most of the smaller stuff around them. As a result, most dwarf planets are simply the largest members of a swarm of bodies like the asteroid belt. So far, there are 5 officially recognized dwarf planets. The first of these discovered was Ceres, the largest asteroid. Next is Pluto, one of the largest known objects in the Kuiper belt. Both Ceres and Pluto were considered planets for many years after they were discovered and before it was realized that they were simply part of a swarm of bodies. Next up is Eris, which has the largest mass of any of the dwarf planets. Eris is much further from the Sun than Pluto, so it's harder to map out. You can see the faint point beside it that is its moon. The next one is Haumea, which is also in the Kuiper belt. You may be wondering about its shape. It's more egg-shaped rather than spherical. But that's a result of the fact that it spins in just under 4 hours. If it wasn't spinning so fast, it would be spherical too. It may be that Haumea was hit by some other body off-center, and this gave it its fast spin. The 2 moons that orbit it may have been knocked off of Haumea at the same time. Lastly, we have Makemake, which is also part of the Kuiper belt. There are many more candidate objects to add to the list of dwarf planets. In most cases, they're hard to observe because of their distance, so astronomers aren't sure if they're spherical, though they are big enough to count from the size criteria we described earlier. The first 2 objects on this painting are Haumea and Makemake, so they've already been added to the dwarf planet list. All but the last 3 objects here are beyond the orbit of Neptune. These last 3 include Vesta, which is currently being studied up close to see if it really is mainly shaped by gravity so that it could qualify as a dwarf planet. The status of Pluto has been a subject of debate now for many years. When it was discovered in 1930, it was considered a planet. However, when astronomers tried to develop an internally consistent definition of a planet, they found that it was hard to include Pluto without including many more bodies as well, possibly all of the dwarf planets. So here is your chance to decide if Pluto should be considered a planet. To do this, you should come up with what the definition of a planet should be. There are lots of things that you could consider in your definition, including size, location, shape, mass, moons, composition, etc. Try not to just pick arbitrary numbers in your definition. If possible, you should have a definition that shows a planet is physically different from other bodies in the solar system. Be creative here. Don't just follow the definition that currently exists. Once you have a definition, you should figure out which bodies would count as planets and which ones wouldn't. You may need to look up information in your textbook or online. Now let's take a different approach to looking at our solar system. Instead of focusing on the individual bodies, I'd like to look over the big trends that describe our solar system. In other words, if a space alien showed up at your door and asked for a brief description of this solar system, how could you give them an overall picture of what it's like? One of the key reasons this is important is because of the role it will play in our next chapter on the formation of the solar system. Any model of how the solar system forms should make sense of these trends. It should be able to explain why we see the patterns we see. The 4 trends are patterns of planetary motion, the 2 types of planets in the solar system, the abundance of small bodies, and the exceptional objects. Let's look at each of these. The first trend is the solar system's patterns of motion. When we look at the objects orbiting around the Sun, we see that they aren't random. Most things go around the Sun in the same direction, and the largest ones orbit very close to the same plane. We can see that in this edge-on picture of orbits. As we look to smaller bodies, their orbits are more scattered around this plane, but it's still usually in the same direction. In addition, the Sun spins in this direction. Clearly, there's something about this direction of motion that was very fundamental to the processes that formed the solar system. Now have a look at the planets in your mystery solar system. If you're working with a group, compare your planets with the ones others in your group have. Among all the worlds in your systems, decide which is the largest terrestrial planet and which is the smallest Jovian, and explain how you can tell. You'll need to look at the masses, distances from the star, and if you calculated them, the densities as well. It's also possible that one or more of the worlds won't seem to fit either category. Too small for Jovian and too far from the star for terrestrial, maybe the wrong density for either. If any of the planets in your systems don't appear to fit either category, say which ones and why. Also, make sure you say which mystery solar systems you're looking at. The next major trend deals with the presence of small bodies in the solar system. As we've already seen, there are huge numbers of these. The smaller the size, the more of them there are. In fact, it seems that every part of the solar system where a small body could remain in orbit for billions of years has small bodies in it. Obviously, however our solar system formed, it was good at producing lots of small stuff.
Here is a statement about the objects in our solar system. Explain whether or not this makes sense. If it does, give examples to support that. If it doesn't, then give examples that don't support this statement.
The last major trend to notice is that there are things that don't fit the major patterns. There are bodies with unusual compositions, like the Earth's moon, with very little metal, or Mercury with far too much. There are planets that are spinning at odd angles, like Uranus. These exceptions tell us that however the solar system formed, it was not so orderly that there was an opportunity for random, one-off events.
This making sense table will help you keep track of the properties of some of the worlds we discuss most frequently in this course. Fill in the first 3 columns of this table for as many worlds as you can now. Keep it and update every time we address a new column. You'll find this page useful for doing homework and reviewing for exams. Depending on your section, you may be required to submit a copy of the completed version for credit.